is the last talk of the season, or the last meetup of the season. We're going to come back in September. We're actually moving, so when you guys come to our next meetup, we will be in our new location at 455 Phillip. Is that the right address?
I know it's on Phillip Street.
It's on Phillip. If you used to work at BlackBerry, it's in room 9. Yeah. Otherwise, it's at the end of Phillip Street, right beside the Tim Hortons. We're pretty excited. We're going to have more than double the space there, which is really exciting because some people like me are sitting beside the bathroom. Because we're growing. And Lisa doesn't even have it. Oh, you have a desk right now.
Right now.
A card table. It's great. Yeah, so we're actually moving in June, so that's why we're not going to do a June event this year. It will be a little too hard for us to move and then get the space up to ready for moving. And then we just thought, like, with the summer we would take a pause because I think we're already seeing it today with the weather being nice. People are less wanting to come out and sit inside. Although I did advertise today that there was air conditioning in here in case, that enticed people to come because it's pretty hot outside.
It's a pack of jokes from the roof.
Yeah. So, all right. So tonight we have Tim speaking. I forgot to do all the intro stuff, so there we go. You can introduce yourself.
Sure.
And I'll let him get going, and then obviously this is always like ask questions and very informal kind of thing. So hopefully we all learn something today.
That's what.
That's yours. I don't know why I'm taking your
455
one.
Phillip.
Sorry. No, I have one here. I'm just a little bit off today.
Thanks for coming out. Today I'm going to talk about a particular category of vulnerabilities I think most developers don't usually think about. So if you're going to be implementing some sort of a cryptographic algorithm, like say RSA or elliptic curve operations, then this is something you need to be aware of. So I'm hoping this talk to do two things. First of all, I want to convince you that timing attacks are actually a real problem, because people don't understand that they are. And second of all, I want to introduce you to a style of coding that can prevent information leaks. So first of all, a quick little example here. So this is a very basic function that just compares an API key. So we have some sort of API key that's provided as an input, and then we have the expected key, what it's supposed to be. And then we do some comparison, see if it's right. If it's not right, we throw an error. Now I wrote this in JavaScript, but I mean, it could be any language really. It could be C, Python, Rust, doesn't really matter. There's nothing, I'm not trying to trick you here. There's no special JavaScript quirk or whatever. It's just a very basic function. So there's actually a vulnerability here, and the vulnerability has to do with how we do a string comparison. So if an attacker knows about this, they can provide a bunch of different API keys as input and eventually figure out what the expected key is supposed to be. So in order to understand this, we need to take a quick little detour and look at how does string comparison actually work? How does it actually implement in the language? So I'm going to write sort of kind of a pseudocode type function. Basically, we're going to implement the string equality function. So we're going to have a function called equals. We'll take two strings, string 1 and string 2. And again, it's going to be JavaScript, but it could be any language. This is roughly what most languages do. So first of all, what we do is you check, okay, are the strings the same length? If they're not the same length, then obviously they're different, so we can return false right away. Second of all, we can look through the strings and go first character, second character, third character. Is there any difference? And as soon as we find characters that don't match, like the third character, they're different, so we can return false right away. And lastly, all right, they're all the same, so therefore we can return true. So that's a pretty straightforward function. I hope you understand that pretty well. So I want you to consider this. Does this function always take the same amount of time to execute? Well, the answer is pretty clearly no, because it would depend on what the input strings are, right? If the input strings are a different length, then right away we can return false. But if the input strings are the same length, and maybe the first 500 characters are all the same, then we have to iterate through the first 500, get to 500 first, and then we can return false. So that would take much longer. So these differences are pretty small, but they are actually measurable. They're measurable if you use the right techniques. All right, so that concludes our little detour there on string comparison. So back to our example code. Let's look at how we can actually exploit this as an attacker. So we're going to assume our API key looks like this. This is a fairly typical API key format. Base 16, so 16 different possible characters for each character. So the first thing the attacker will do is they'll try 16 different keys, 0 through F. Now I have a bunch of X's here. This could be any character though, it doesn't really matter. What they'll find is that one of these 16 attempts will take slightly longer. And the reason for that is that because the correct key has a 6 at the beginning, that for loop will have to do one more iteration. So it'll compare the first characters and find, oh, they're the same, and then go to the second characters, and then it can return false. Whereas all the other attempts, it can return false right away on the first iteration of the for loop. So now the attacker knows the first character, and they can repeat this process and do another 16 attempts, 0 through F again, for the second character. And again, they'll find that one takes slightly longer. So now they can just repeat this and extract the key, one character at a time, until they have the entire key. So that's the basic timing attack. So first lesson I want you to take away from this talk is that timing differences can reveal information that you do not think your code was revealing. So usually at this point, I get a question along the lines of, well, can you really measure that? Like, these timing differences are very small, so is it actually possible to measure these differences? And the answer here depends on a number of factors. It depends on what platform you're using, what language you're using, and also in the context of a server, it depends on the hosting environment. So if you're in a shared hosting environment like, say, Amazon EC2, then that's very helpful for the attacker, because the attacker can rent a server in the same data center as your server, and now they have a low latency LAN connection directly to your hardware. So that's great if you want to take precise timing measurements. So the rest of my talk is going to be about how do we fix this problem. So I'm going to assume that you actually are in a context and an environment where timing attacks are possible and you can measure these timing differences precisely, which, to be fair, like in many cases is not the case, right? Sometimes just you don't need to worry about these issues. But I'm going to assume you do. So the first thing that everybody always comes up with is, why don't we just sleep for a random amount of time? All right, so add some sleep commands, add some random delays to our code, and now the execution time will be randomized, so the attacker can't learn anything. Well, there's a problem with that. Unfortunately, it's vulnerable to a thing called statistics. So you can take a bunch of measurements and record the execution time over a bunch of attempts, and then you can do, say, like an average to figure out which one's longer on average. Or you can do something fancier. You can do, there's something called a box test that does some fancy math to figure out which probability distribution is actually different. So that's the first problem. Another problem is that people generally want their code to be fast. And sleeping is kind of the opposite of fast, so that's not particularly useful. But there's actually a much bigger issue with this approach. And the issue has to do with the fact that modern computers don't just do one thing at a time. They actually multitask. So you have thousands of processes all running in parallel. Well, not actually parallel. You have an operating system scheduler that decides, okay, this process goes on that CPU core, that process goes on that CPU core for that amount of time, and so forth. So you might wonder, well, how does the scheduler actually decide which process should get which CPU core and when? One of the factors it looks at is that process sleeping? If the process is sleeping, then obviously it doesn't need to be on a CPU core right now. It doesn't need CPU time, it's just a waste. So what that means is that if your process is spending more time asleep and less time doing actual computation, then there's more CPU time available for other processes on the same hardware. And that means if an attacker can observe how much work other processes are getting done, then they can infer how much time your process spent sleeping, and therefore infer how much time your process actually spent doing a computation, and now we're back to being vulnerable again, right? We can get precise timing measurements. So this is kind of a long way of saying that what your program does will affect the performance of other programs on the same hardware. Your code will have these subtle but measurable interference patterns on other processes. And this is not only within the context of an operating system, this actually happens across virtual machines too on the same hardware. So in a shared hosting environment, again like EC2, you can actually record these interference patterns coming from other people's virtual machines. So I've talked about one case of interference pattern before, a process state, but there are actually a number of different sources of interference. And I don't have time to go all of these today because this is actually like an entire subcategory of academia. Like there are hundreds of papers looking at this sort of thing. So obviously I can't go through all, but I want to cover a couple key ones. So one is around memory bandwidth, which is limited. So if your process is reading and writing a lot of data from and to memory, then that will impact other processes if they're also doing a lot of memory access. So that's one way you can have contention on a shared resource. Another issue I need to highlight is around CPU caches. So if your process is using a certain part of the CPU cache, then other processes might be able to tell that that part of the CPU cache is being used. So that can reveal surprising amount of information. Let's say you have an array, and you're accessing a particular element of that array, element number 5, let's say. Then another process on the same hardware might be able to tell that you accessed element number 5. They won't necessarily be able to see what's in element number 5, but they can see it was number 5 and not number 6. So that can be a major issue at times. So, okay, this seems bad. You might be wondering, well, will this get fixed in hardware? Because it feels like a hardware problem, right? It feels like a hardware security problem. And unfortunately, the answer is probably not, because everything on the previous slide was about either improving performance or reducing cost. So as long as people still want their CPUs to be cheap and fast, then this is probably not going to get fixed anytime soon. So lesson number 2 here that I want you to take away is that these interference patterns can also reveal secrets. They can reveal information about what your program is doing and what it's processing. So,
A question. So you mentioned that other process can tell that you accessed element 5 in the array.
yep.
Can you give details? Because you could have like a busy task scheduler, and I mean, you can access, for example, element 1,000 and then 1,000,000 and then 5. So how can you know when you access the element 5?
So the way that works is, it gets into the details of how the CPU cache works. So what will happen is the other process that's trying to observe what your process is doing. So this is mainly in the context of like you have multiple VMs on the same hardware, right? So you have maybe one VM belongs to someone else, and one VM is yours, doing sensitive information processing. So in the other VM, what you would do is you would fill up a bunch of stuff in the CPU cache. So you get the CPU cache into a known state, and then you allow the process you're attacking, my process, to do some sort of processing and do a computation, access an element of the array, let's say element number 5, and then that will cause a certain piece of the CPU cache to be evicted. So now the process that's doing the monitoring can observe the fact that, oh, that piece of the CPU cache got evicted, and it can tell, oh, that corresponds to probably element number 5. There's a bit of like guesswork involved, obviously, right? But that's generally how it works. Does that answer your question?
Yes, but what's the name of this? I mean, it is like...
It's called a cache timing attack.
Oh, okay.
Yeah, if you look up like cache bleed, for example, is one example of that. Yeah, lots of papers on that. So
Okay.
It also depends like what level of cache you're attacking and stuff, and whether you're on the same CPU core. It helps a lot if you have hyper-threading enabled or simultaneous multi-threading, because that way you can have multiple processes on the same core at the same time. That makes things a lot easier. But yeah, again, like this field goes very deep, very fast, like in terms of getting like reliable execution and exploitation.
There is a tool for this, or it's just...
Lots of tools. Yeah, I mean, like it really depends on like what code you're targeting and how the code works, and the details of like whether it's hyperthreading or whether you're across VMs, or like it depends a lot on the context. So yeah, you basically have to, when you write exploits for this type of thing, you basically have to target like a specific type of hardware and a specific application that you're trying to target. Like it gets very specific in how you actually exploit it. So yeah, and there isn't much in terms of like generic frameworks for building exploits yet, which we kind of need if there was, but there's not. So okay, from this point on, I'm going to be talking about a solution here. So a solution that actually works. Of course, the solution is going to involve managing the execution time of your code, but also the hardware resource usage. So I'm going to give you 4 steps. And step number 1 is to figure out what variables are actually sensitive. What variables do you actually care about concealing? Because the reality is that in most applications, most variables are not really that sensitive. It's fine if you leave them. So once we identify which values we actually want to keep secret, then we can try to eliminate this relationship between the secret values and our resource usage. So the idea is that no matter what we do, if we're executing code, we're going to have these interference patterns happening. We can't avoid that. But what we can try to do is we can try to make sure that there's no correlation between the interference pattern and the values that we want to keep secret. So as long as there's no correlation, no relationship between the two, then the attacker can record the interference patterns, but they won't learn any useful information. So step 2 is the first rule that we have to follow. So the idea here is that we have control flow, right? So we have control flow around like if statements, while loops, for loops, whatever. We need to make sure that this control flow is not affected in any way by a value that is secret. So here's a bad example. So we have an encryption key, we're accessing a particular bit of that encryption key, and then we have an if statement that uses that bit as a condition. Any condition we use in an if statement must not be something that's secret. We have to assume that an attacker can learn the value of that condition. So in this case, the attacker would learn what bit at index 5 is, so this encryption key. So that's bad. So again, we can use if statements. If statements are fine as long as the conditions are not secret. We have to assume the conditions are public information. And same with loops, same with while loops, for loops, and so forth. So step number 3 is make sure that we eliminate any secret memory addresses. So the idea here is that anytime we access a particular address in memory in terms of reading or writing, we have to assume that the attacker can figure out what address that was. So a common example here would be accessing a particular element of an array. So we have an array hexChars, and we're accessing an index here. And this index is a secret number. So this is bad. We're not allowed to do that. And same thing with writing to an array, because of cache time attacks. And the last step here is just to avoid variable time operations. So there are particular CPU instructions that's on virtually every modern processor are not constant time. So division is the most common example here. Division on pretty much every modern processor will be faster if you're working with smaller numbers, because they've coded in a faster path for smaller numbers, which is kind of nice for performance, but again, that adds like variability to your execution time, so that can cause information leaks. All right, so that's about it. So if we actually follow these rules, follow these steps, our code ends up looking kind of weird. So here's a little silly example function. And this is just kind of basic, but it's, you take a value x, which is an integer, and then we either add 5 to it or we double it, right, based on what this value here is. So what if we wanted to actually conceal whether we're adding 5 or we're doubling? Right, we want to conceal which actually happened. Now, we have an implicit if statement here. This ternary operator is implicitly an if statement, so our control flow is not secret. Our control flow will reveal which one we actually did. So if we want to clean that up, we end up something like this. So I don't have time to explain this in full detail, but basically what's happening here is...
Sure you do.
Do I?
Yeah, totally do.
Okay, sure.
Dive in.
All right, so basically what we do here is we calculate the 2 possible inputs, right? So we have 2 times x and x plus 5. And then we do some bit twiddling to figure out, to produce the right value. So here we have the Boolean add, and we're implicitly, this is JavaScript, so we're implicitly turning this into an integer here. This will produce either a value that is all zeros or all ones in terms of the binary. And then we flip all the bits here to produce the opposite, right? So if this is all zeros, mass 2 will be all ones. Or if mass 1 is all ones, then mass 2 will be all zeros. And then we AND these bitwise with these 2 values here. All right, so basically what we end up doing is we end up doing 0 and double, or 1 and x at 5, or we end up doing 1 and x double, or 0 and x 5. Right, so we're selecting one or the other here. So that's how that works. So you'll notice here that there's no if statement, right? There's no if statement involved, but it's effectively doing an if statement. And because this control flow is just pretty much a straight line, right? There's no fancy control flow going on. This follows our first rule of having no secret control flow. And all the memory addresses here are constants, and there's no variable time operations. Good question?
Isn't or an if statement? Like, won't it short circuit, and if mass 1 and double is true, then it stops?
So this is a bitwise, right? So you'd have like 2 pipes if it were a Boolean operation, but this is a bitwise operation here. So these are actually integers, and we're just ORing together these integers like a bitwise.
It's always do everything.
Yep. Yeah, because so this is a Boolean here, but then as soon as we subtract 1 here, now this is an int, that's an int, that's an int, right? So everything's just integer math from this point on. Any other questions? Okay. So let's see. Yeah, so that works. That's great. This code works. Only one problem. There's a little catch, unfortunately. And the catch is that compilers are really smart. Compilers are way too smart. So many compilers are capable of looking at code like this and seeing through what we're trying to hide and optimizing this back into an if statement. I kid you not. So this is an excerpt from the LLVM source code. LLVM is a compiler toolkit that's used in like Clang and Rust compiler and Swift compiler and a lot of popular compilers. And I spent a lot of time reading through it. And this is a particular optimization it does. So match, select from and or. Select is like an if statement in LLVM. So it will look for something that looks like this. A and C or B and D. And sure enough, oh yeah, right, that's like basically what we have here. And it will see exactly what we're doing and optimize this back into something that looks exactly like this. Like exactly, perfectly the exact same. So yeah, thanks LLVM, that's great. So what do we do with this? We have a few options. We can just forget about using high-level languages, like not even C, and just use assembly. That's kind of not great. Or we could use a high-level language, but then try to like compile it into the machine code, and then look at the machine code and say, okay, well, is this actually what we wanted to do? And try to audit that somehow. That's really painful and hard, but that's often what people end up doing. That's not great either because, well, what if we want to do something in a dynamic language, like JavaScript or Java? Well, that doesn't work too well because in the case of Java, we're compiling into JVM bytecode, and then the bytecode gets compiled at runtime into machine code. So we don't even know what's going to happen at runtime. It depends on the version of the JVM or like the conditions at runtime that the JVM decides to optimize under. So that's not a great solution either.
You cannot disable optimization?
But you could, but then people want their code to be fast. That's the thing. Like, we spent years, people spent years avoiding deploying SSL because they thought it was slow. And now it's like, okay, so I guess people in the cryptography community finally learned that, okay, we have to make our code fast, otherwise people don't use it. But yeah, so you can do stuff around disabling optimizations, but generally people will just not use your code. It's been our experience so far. Or it will just get really slow. Because if you just disable enough optimizations to prevent this from being an issue, then it gets insanely slow. I'll talk about that a little bit later, actually.
There is no compiler that says optimize except these things.
There's not, no. Yeah, that's the thing. So like, we really need compilers to understand this problem. Right now, compilers are completely oblivious to this idea of timing information leaks. So ideally, our compiler is
every other time it's not doing it for security reasons you want it to optimize. It's a little bit difficult to tell it like when
Right.
it should optimize and when it shouldn't optimize.
Well, that's the thing. Like, ideally, what LLVM would do is it would allow you to specify, okay, this variable I want protection on.
Yeah,
that
it's
variable I
crypto
don't.
mode or something.
Yeah, like be able to flag which ones.
Yeah,
Which
that makes sense.
part of the reason I want to do this talk is that someone in this room hopefully will be a compiler person someday, and they'll be like, oh, I can do that. I can work on that. That's my dream.
I think I kind of wanted to do the other thing. Like, I write a regular old if statement, and then it turns it into your bizarre code.
Oh yeah, just for
Like, I write a regular if statement, I say, please protect these variables.
Right.
And then it does the other pattern matching to actually turn it from, here's an if statement. for
Readable
numbers.
code to like.
Right.
Yeah, because it seems dumb to try and
Right.
expect a human being to do a good job of being very consistent in this.
Well, hang in there, because I have something for you a little bit later in this presentation.
Your dreams might come true.
It might happen. So this is the part of the presentation where I shamelessly plug my own solution. Which, yes, it does indeed have a utility function called select that allows you to very readably write if statements. So you will enjoy that. So basically how Rust Timing Shield works, it's a framework for writing Rust code and preventing these sorts of information leaks. So the way it works is you mark certain variables that need protection, and then it will give you errors at compile time if it detects an information leak. So the way it works is that in Rust you normally have these integer types, so you have like I8, I16, I32, and so forth. Those are the standard Rust integer types, but with Rust Timing Shield you get these additional integer types. TP-I8, TP-I16, TP-I32. TP stands for timing protected. So if you use these time protected integer types instead, then they work just like normal integer types, but you get this additional protection. So you can do things like you can add to TP-U16s just fine, you can use plus, it works just like normal integer type, but then if you try to do something with it that would create an information leak, it won't compile. So a quick example of how this looks in some real code. So let's say we have a function called setup encryption. So it'll take one parameter, call it a secret key, and the secret key is just a sequence of bytes, so a sequence of U8s in Rust terminology. So if we want to use Rust Timing Shield instead, then we'll just replace U8 with TP-U8, time protected U8. So now we have a sequence of time protected bytes. So now we're not allowed to create any information leaks. unless we explicitly opt out of the protection, which we can do. So we can go about using this just how we would normally. So we can access the first byte just by accessing index 0, that's normal Rust. But then if we try to do something with it that's not allowed, like let's say we try to have an if statement with a secret condition, this will not compile. It will not compile unless we can explicitly flag it and say, okay, I want to leak this value, I want to leak this Boolean. But if we don't do anything special, then it will just say, hey, that's an information leak, so I'm not going to let you do that. Similarly, if we have a secret memory address, we can try to use this as an array index. That will not compile either. And lastly, if we try to use it with a variable time operation, like say division, then that will not compile. So basically, if we break any of those rules I outlined earlier, then Rust timing shield will just say, hey, you shouldn't do that. And of course, it only applies to the variables that we specifically use a TP type with. If we had used a normal U8 here, then it would work just fine. This would compile, because it's not protected. So you might be wondering at this point, well, I talked earlier about compiler optimizations causing issues, so how does Rust timing shield actually work? Well, the answer is not particularly great, but basically what I did was I spent a lot of time reading LLVM source code to understand what optimizations it would actually do. And then based on that understanding, I built a whitelist of safe operations for each type. So I understood like how to avoid those optimizations that cause issues. And then I did a little work within line assembly to block optimizations that would be a problem. So this works. It's not ideal though, because if LLVM introduces new optimizations in the future, then I might have to rewrite Rust timing shield to work around that, right? So it's really dependent on implementation details of the compiler, which is not ideal. Ideally, the compiler would understand this stuff already, and I wouldn't have to teach it about it. So, if you want more information on Rust timing shield, this is my website. You can find it there. Lots of documentation on that, and explanations of how it works. Just Google Rust timing shield, and it'll come up. So I was hoping in this talk to get across a couple ideas. Mainly, I wanted to introduce the idea of how execution time and hardware resource usage can reveal a lot of information that you do not think your code is revealing. So you can prevent these information leaks with these 4 steps: identifying secret values, and then eliminating any secret control flow, any secret memory locations, and avoiding using a variable time operations like division on secret values. So I want to close by saying, like, we really need more people to work on this problem. I want compiler people to actually think about this and hopefully add features to the compilers to make this easier to work with. We need better tools, we need better frameworks, we need more people thinking about this and trying to find solutions to it. So that's about all I've got. If you're interested in this sort of stuff, I blog about cryptography on my website, josephmindex.ca. I'm also at McLean0 on Twitter. You can follow me there. All right, thanks for listening.
Cool, thank you.
Questions?
I just wonder, all this just to randomize the execution time?
Not randomize. Remove the relationship between,
Yeah, randomization, remove the relationship. Anything random.
randomization doesn't always remove the relationship though, right? That's the key thing.
So how about if, for example, like the load balancer, but make function balancer or distributor, we have, for example, more than one version of the function coded differently
Right.
with different execution time.
Okay.
And like a load balancer, something randomly, like assume each function that implemented in different, with different implementation, and the integer for the case statement, random, sometimes bring you here or there, to randomize the time.
So
this
that,
also.
that might help with execution time. The issue comes around hardware resource usage, because there are some pretty big leaks that can happen that way. So specifically, I'm thinking of a paper from 2009 that attacked an RSA implementation. And the way it worked, it was very impressive because basically what they showed was that with one execution of an RSA encryption, like one encryption operation, and another process listening in another VM, it could record enough of the hardware usage information to figure out the entire key from one execution of the encryption function. So the way it does that is, I talked a little bit earlier about the cache timing attacks, right? So you monitor what's going on in terms of hardware usage, and it's able to monitor in enough detail that it can extract enough bits of the key to recover the entire key. So with that sort of issue around, the idea around like randomizing which function is being executed, well, you probably, I guess you'd have a finite number of functions to execute, right? Maybe in the order of like 10 or something like that? Or how many are you thinking of?
No, maybe 5, just random, and each one with different implementation that incur different execution time
Right.
with respect to other. I rotate it here and there every time. Just random number generator, and they bring you to different implementations of the same function.
Right. So yeah, the issue there would be that in the case of Harvard resource use students, another process could probably identify pretty easily in real time which function is being executed based on stuff in the cache.
But better than the delay, like if we said if we impose delay time and
Like adding a sleep command or something like that. Like, I mean, that's still like with Harvard resource usage, you get the interference patterns very clearly. Right? You can very easily identify which code path is being executed, what decisions are being made in terms of like an if condition, like your control flow. You can identify what memory address is being accessed. It's like all that stuff shows through pretty easily in that context. So I don't think that would help that much. Like, it might obfuscate things a little bit. It would be more useful if the codes, if you had like, let's say 10 different, or five or 10 different implementations of the function, and then you kept that code secret maybe. Maybe that would make things harder, because then the attacker would have to actually, yeah.
Yeah, it seems like it would only work if the code was secret. Like if it's open source or any public things that other people can know about, they could probably figure it out.
Then I will treat every different functions as if you are adding a random timing delay.
Yeah.
And in fact, it won't be as random as a random generator. A random generator can have hundreds of numbers. You will have only 10, how many functions, 10 different random additions for the timing. And from there, we'll go to the statistical attack.
Yeah, that's true. You're basically overlaying 5
that's
different
how
operating
I'll
instructions.
yeah.
Yeah. So,
What do you think is the performance penalty
penalty?
Yeah.
In the case of
of a solution like the
Rust
time
Shield?
protected?
it's very minimal. So I thought very carefully about how to get good performance. So there's another solution prior to Rust Timing Shield in Rust. I think it was called the Deco or something like that. I forget what it was called. But basically how it did it was it's similarly had, I think it similarly had types like these, but the way it worked was it implemented things like add and subtract entirely using inline assembly. And the way inline assembly works with LLVM is that it's basically like a black box. So LLVM sees, okay, there's some inline assembly here, I'm going to spit that directly out into the machine code. The problem with that is that it prevents any kind of optimization from happening, like even the most basic optimizations. So if they implement add as like an x86 add instruction, right? So add register, register. So then let's say you have an expression that's something like x plus 1, right? So you can imagine x plus 1 would normally compile into like an increment instruction, right? Increment a register. Well, if you implement add in inline assembly, then what you'll actually end up outputting is something like move register 1, right? So load 1 into a register, and then use that register to add, right? So it completely prevents like all these sorts of like constant folding and all these optimizations you normally want the compiler to do. So it ends up being horribly slow. In the case of Rust Timing Shield, I minimize that as much as possible. It uses very little inline assembly. There's only inline assembly around handling booleans. So booleans was the case where I pretty much had to, because that's where it got way too smart. So yeah, so there's not much performance overhead in using Rust Timing Shield over just trying to do it yourself in Rust. But in some cases when you have to like do crazy stuff, right? Like if you're doing like this kind of stuff, then yeah, I mean, versus like a normal if statement, there is overhead. So it's just the techniques have overhead, the framework doesn't. I guess is what I'm trying to say, for the most part.
With the slide with the CPU timing, you listed other timing, I guess, attacks.
This one here?
Yeah. Do you have on your website the references to this, or?
My website, not so much. There's a pretty good survey paper. I think if you Google, I think it's called A Survey of Microarchitectural Timing Attacks. It's only a few years old now at this point. It's pretty good. It goes through like pretty much all of these. Yeah, I recommend looking at that. Microarchitectural timing attacks, that's the key word there.
Why Rust?
Ooh, that's a good question. So, Rust for me is a very good, it makes a lot of trade-offs in the language that are very good for this kind of stuff I want to do. So I do cryptography engineering, so I care a lot about just like quality and preventing bugs, obviously, but I also care about performance. So I often do work that's ends up being highly performance sensitive. So Rust has the good mix of generally nudging you towards things that are both like solutions that are both correct and fast. Like it generally makes performance trade-offs explicit in the language, so it's very useful that way. I guess it's also it's low level in a way that's kind of C tends to be, so that way you get a degree of control. But it also lets you do cool stuff like implementing your own integer types, for example, right? Which some languages can't do. So yeah, I think it's the right mix of like low level control versus like high level expressivity. It's very nice.
There is an interesting talk at Google I/O this year. A professor, well-known professor of computer architecture, he made the point that the general computing architectures, hardware architecture, I mean, are by their nature exposing you to vulnerabilities. And he made a point to design dedicated domain-specific hardware architecture. It's very interesting how he put.
Send that to me after. I'll watch it.
Okay.
Yeah.
So this, I don't know any Rust, so maybe this is a dumb question.
No, sure.
Is there, have you eliminated the problem of like taint in the sense that I've declared this TP int 16 and I'm going to copy it to a regular uint and I'm going to do bad stuff with the regular uint? Does Rust prevent me from doing things like that, or does your tool prevent me from doing things like that?
The tool does. So once the way it works is that you have some sort of input, maybe you receive it from the network, or you receive it from a user or whatever, and then you explicitly wrap it into a TP type, and you do that with a protect method. And then once it's wrapped, you have to explicitly unwrap it in order to get back the original type. So if you're passing it around, you're copying it places, or you're doing, let's say you have a TP type plus a TP type, you get a TP type out of that. Right, so it continues to be TP until you explicitly unwrap it.
But if I add a TP type and a regular type, can I get a TP type?
Yes.
Maybe I'm looking at this the wrong way, but I'm kind of curious, you're trying to keep as much as possible from leaking. And one of the things that you said, the obvious thing to do is to make it do sleep cycles.
Right.
Right. Instead of doing that, what would be the advantage of going this route versus adding noise? Like having
Noise.
a simple loop to just randomize the amount of time, so you're not sleeping, so you're doing some form of work, you're dumping stuff to registers.
Oh, I see.
Just enough to obfuscate.
So I mean, you still have statistics, right? Statistics is still a problem there. So you end up with this sort of trade-off between how much time you spend sleeping and how much security you get, right? So
Yeah,
maybe
no sleeping.
sorry, not sleeping, spin locking, I guess, right? That's sort of the idea, right?
Yeah.
So you end up in this trade-off between how long you spend in that busy loop versus how much security you can actually get, right? Because basically, the more noise you add, it just increases the number of samples the attacker has to take, right? So maybe you can increase that number to a point that doesn't matter anymore, but that adds a lot of overhead, right? So that's the first issue, overhead. Second issue is that it doesn't prevent these interference patterns, right? The issue around hardware interference patterns, that still occurs. So an attacker can potentially observe that, okay, your code has moved into this spot, it's moved into the busy loop now. And now that it knows that, I mean, it's help. So
you guys don't want to see pictures of my family?
Okay.
Well, probably we can just like turn the light on anyway. Or no, sometimes you're going into your slides still. That's right. Sorry.
Yeah, so generally with the hardware usage interference patterns, a lot of information is available there. So you can see, for example, which point in the code is currently being executed. Right, so if you reserve that, then you can observe, okay, the code is now moved into the busy loop. So therefore you can infer, okay, it stopped doing the actual execution, and you can get an idea of the execution time that way.
I mean, adding it right into the function.
Yeah, so I
You'll
think I
never-
know where you're going, Lee. So for example, when I was at BlackBerry, we were running an AES algorithm, and we were working with Professor Kathy Bodies, I can never say it right, at the university. And she was figuring out the key based on electromagnetic forces, right?
Yep.
So similar but different, right? So she could figure out when you hit the key based on an electronic pulse that was a bit higher than
Very
not.
similar, yeah.
So she implemented a countermeasure for that, in which you took AES and you put it in the you can run AES like as a procedural program, or you can run it as tables. So you put a key through a set of S boxes, basically, so matrices, and it does the transformations for you. And so what her paper said to do was to add randomness to the key and add randomness to the tables. And so as you processed it, you couldn't tell anything because it was like all random. And then when it came out at the end, you poured it back with the mask, and you got your key, and they couldn't do the electromagnetic attack on it. So that, by the way, made the AES algorithm 4 times slower than the regular algorithm, and we ran that. I implemented it, and then we ran that on BlackBerries for a few years, and the government would be the ones that had it turned on, so they were getting tired of their BlackBerries being so slow. So then we ended up re-implementing it in assembly, and just took it right down. So it was already, the first implementation was in Java, then we moved it to C, then we moved it to assembly.
Yeah, that's how it goes, yeah.
Yes. Also, by the way, it is not fun to debug your AES algorithm with 16 loops when you've added randomness and you can't check the blocks anymore.
We have a hero here.
It's really not fun at all. But I could imagine that what Lee is trying to say is actually adding randomness into how you're doing the computations, so as not to give these timings away, without not by slowing it down, but by using some kind of like randomization of the arguments itself, or masking them before you go in. So even if it keys off, it's keying off on the wrong computation.
The idea that came to me when I was looking at the string comparison is, rather than go from the first index, like go randomly through the index every time. So like
It's a lot slower.
it's a lot slower, but if you're only doing it for particular things, then it's
So, and the thing is, like, for these types of things, and what we discovered, at BlackBerry, was that people who really, really, really care about their security in this way are okay with things slowing down. They're not okay with it going, like, about 8 times slower, but they are okay with it going slightly slower because they're more paranoid, right? So that's where I think we originally like turned it on for everyone, and then realized it was making BlackBerry slow, and then I was the cause of making BlackBerry slow. Sorry, people. Then we just turned it on if you wanted the extra security.
It's more of an issue in a server context, I think. So that's where you really care about like minimizing overhead and also security. That's what my clients usually hire me for, actually. Just like
I'm
server
just.
context, yeah.
It depends on who the client is, and
Yeah.
what they need and what their purpose is, and I won't tell you how many years ago that was that I did that, and probably at that time only the governments were caring
Right.
about security as much.
Yeah, so the technique you described there is like that's used. It's called blinding. And that's used like for RSA applications pretty commonly. So the idea
Yeah.
is like you have some secret inputs, and then you blind them with some random value. So now you have some values that are okay to leak, right?
Yes.
So you can also like Rust timing shield supports that fairly well too, right? So you just end up working with non-TP types in the middle. That works great. The issue there, of course, is that the blinding process itself still has to be information leak proof, right? You cannot have any information leaks there. So, well, let's look at some kids.
And a dog, and some Easter eggs. Gee, you don't need this anymore. I think I'm turning it off. Because that's just gonna keep.
Is that another form of information leak?
Right there. Right there. Yeah. Screensavers.
Any other questions?
I had one question. I think you sort of hinted at the beginning about hardware and how it's not really going to get fixed at the hardware level.
Right.
So what came to my mind was, as you're going through the code, you're talking about two VMs on the same host, let's say Amazon, right? I don't know how you'd be able to actually identify that you're on the same host. Or what if the target system was encrypted? Would that make any difference?
What would be encrypted there? Like
Like
memory?
the OS, like, let's say the user said, I want to encrypt my OS so that, if Amazon got attacked or something, my data would be semi-protected. Would that make any difference to your performance in trying to analyze things?
Probably. It has to be encrypted to go through the first, doesn't it?
Yeah, it's like, what are you encrypting, I guess? Like you say OS, like.
So let's say you
on
encrypt
disk?
Windows. Let's say it's a
Memory?
Windows or a Linux OS, right?
Right.
And let's say I want to encrypt the OS, and so when I log in, I decrypt it, run my process, they run in the background, but when I log off, it encrypts it. So
Okay.
I'm looking at the physical level, but
Right.
my thinking is, if you have VMs, would that not still apply?
The issue
It's
there.
a runtime attack, right? So
Okay.
it's attacking you while you're doing the execution.
So it'll be
encrypting that-
decrypted while it's
Yeah.
while you're running. Yeah, that's the
Okay.
issue there. Yeah. Which, yeah, there have been different attempts to look at techniques involving encryption with varying levels of success. But you end up often in some trade-offs there that work particularly well. So, yeah, good thought. Else?
If you convert some code to use the protected version,
Mhm.
is there a chance that it would compile but still behave differently, or like, could it affect, like, if you're talking about like a cipher implementation or something, could the code compile as if it doesn't have any of those functions anymore or whatever? Would that affect is there a chance that the behavior of the cipher itself changes?
Like would still
Like,
changes
from
from
some, like, let's say you're counting on some property that for a regular integer, for example, or whatever, and that just happens, but and you were using that was part of the implementation. You were using that knowingly or not. Now, when you're using the protected version, is there a chance that you
Oh, I
lose
see.
this
So sort of like
feature
functionally,
and break
basically.
the cipher without the compiler breaking it at compilation?
If there is, then I messed up pretty bad. Yeah, it should be functionally identical, basically. Rust timing shield should not impact it shouldn't impact the outputs of your code, basically. So if you're adding two integers, then it should add them exactly the same way, right? There shouldn't be any impact there. The only thing it impacts is what optimizations the compiler does to your code, basically. And compiler optimizations are necessarily designed so that same inputs has the same outputs and side effects, right? That's sort of that's the general rule of compiler optimization. So yeah, it shouldn't impact any actual functional besides side channel leakage, besides information leakage. That's your question?
Excellent. Well, thank you, Tim.
All right.
Great, and we'll see everyone hopefully again in September in a new, bigger, less cramped space. Less
luck on
cramped
the
for.
move.
Yeah.
Yeah.
So say good luck to him. IT is going to be working hard on this one.